Welcome to Lecture 5. This week we're going to talk about derivatives of trigonometric functions, the chain rule, and implicit differentiation. First, let's discuss the trigonometric functions. Let me remind you of three formulae. The first one is one that I imagine you're familiar with from high school. Sine of x plus h is sine x cos h plus cos x sine h. And then the second and third formulae are rules that we've proved in previous weeks. The limit as h tends to 0 of sine h over h is equal to 1, and the limit as h tends to 0 of cos h minus 1 over h is equal to 0. Using these three formulae, we're going to calculate the derivative of f of x is equal to sine x. So let's do that now. We're going to use the definition of a derivative. So f prime is the limit as h tends to 0 of f of x plus h minus f of x divided by h. And we're doing that for the function sine x. So we have the limit as h tends to 0 of sine x plus h minus sine x divided by h. Using the first formula from the previous slide, which I'm writing in orange, that's the same as the limit as h tends to 0 of sine x cos h plus cos x sine h minus sine x over h. The second and third formulae from the previous slide I've written in the yellow box at the top. Our aim is to use these two formulae. So our aim is to rearrange the limit that we have so that we can use the two limits that we already know. I want to have a sine h over h, and I want to have a cos h minus 1 over h. Now we almost have that. If we put the sine x terms together first, we have sine x cos h minus 1, and then plus cos x sine h over h. Or writing that a different way, using the sum rule, that's the limit as h tends to 0 as sine x cos h minus 1 over h, plus the limit as h tends to 0 cos x sine h over h. The two terms that I've written in red are constants. X is fixed, we're not changing x, so that means sine x is just a number and cos x is a number. Anytime we have a number inside the limit, we can take it outside of the limit. We can write this as sine x multiplied by the limit as h tends to 0 of cos h minus 1 over h plus cos x, limit as h tends to 0 as sine h over h. And now we have the limits that we know. We know that the limit of cos h minus 1 over h is 0. And we know that the limit of sine h over h is 1. So this is just sine x multiplied by 0 plus cos x multiplied by 1, or cos x. The derivative of sine is equal to cos. We could do the same thing for the derivative of cos. And I'm not going to go through the details here, you can read this in your textbook, but let me just say the idea is the same. We're going to start with the formula, and then we're going to rearrange this so that we have the two limits that we know. The first one is 0, and the second one is 1. Because of this, we find that the derivative of cos x is minus sine x. Why is it minus? The minus comes from the identity cos x plus h is cos x cos h minus sine x sine h. These formulae are important. I'm going to write these as a theorem. The derivative of sine x is equal to cos x, and the derivative of cos x is equal to minus sine x. We're going to do some examples using these formulae, so I'm going to put these two formulae at the top of the slide in a yellow box. For example, differentiate, which is the same as saying find the derivative of y is equal to x squared minus sine x. There's two functions here. There's an x squared function and there's a sine x function. The derivative of x squared is 2x and the derivative of sine x is cos x. So the answer to this question is 2x minus cos x. Another example. Differentiate y is equal to x squared sine x. Now we have function multiplied by function. So for this type of question, we're going to use the product rule. And let me just remind you, the product rule is that the derivative of uv is u prime v plus uv prime. We differentiate the first function, we leave the second function as it is, and then plus, leave the first function as it is, and then differentiate the second function. Or if you want to, you can do them in the other order. It doesn't matter because a plus b is the same as b plus a. We could do uv prime plus u prime v if we wanted to. Here, u is the function x squared and v is the function sine x. So here we go. Y prime is the derivative of x squared and then leave sine x as it is, plus leave x squared as it is and then differentiate sine x. So that's 2x sine x plus x squared cos x. Differentiate y is equal to sine x divided by x. This is a quotient rule question. I'm going to remind you of the quotient rule. The derivative of u divided by v is u prime v minus, in the product rule it's plus, but in the quotient rule we have minus uv prime divided by v squared. Here u is the function sine x and v is the function x. And here's the calculation. Y prime is equal to, differentiate the function on top, so sine x prime, and then the function on the bottom just as it is, x, minus, leave the function on the top as it is, so just sine x, multiply it by the derivative of the function on the bottom, x prime, and then everything is divided by the bottom squared, so everything is divided by x squared. Because the derivative of sine x is cos x and the derivative of x is 1, the answer to this question is x cos x minus 1 sine x divided by x squared. And of course, we don't need the 1 here. Differentiate y is equal to 5x plus cos x. Just use the sum rule. We have the derivative of 5x, which is 5, plus the derivative of cos x, which is minus sine x. So the answer is 5 minus sine x. Differentiate y is equal to sine x cos x. This is another product rule question. We have function multiplied by function. Differentiate one of them and leave the other function as it is, and then do plus, and then do the opposite. Leave the other one as it is and differentiate that function. So derivative of sine x plus cos x multiplied by cos x plus sine x derivative of cos x. So that's cos squared x minus sine squared x. Differentiate y is equal to cos x divided by 1 minus sine x. This is a quotient rule question. So the derivative is going to be u prime v minus uv prime divided by v squared, which for us is derivative of cos multiplied by 1 minus sine x, and then minus cos x, derivative of 1 minus sine x, and then everything is divided by 1 minus sine x squared. Derivative of cos is minus sine. The derivative of 1 minus sine x is 0 minus cos x. Now we've done the hard work, now we've done the differentiation. All that's left is to simplify this to get to a nice, easy final answer. There's another nice example in your textbook, but I'll leave that for you to read. Please read example 3 in section 3.5 in your textbook when you do your studies. So that's sine and cos, but there are 6 trigonometric functions. The next one we should look at is the tangent function. And I'm going to tell you the formula first. The derivative of tan x is equal to sec squared x. Let's prove this. We can prove this using the quotient rule. Why? Because tan just means sine divided by cos. We know the derivative of sine, we know the derivative of cos, and we know how to do the derivative of a function divided by a function. That's derivative of sine, cos, minus sine, derivative of cos, all divided by cos squared. So cos, minus sine divided by cos squared, or cos squared plus sine squared divided by cos squared. And as I think everybody remembers, cos squared plus sine squared is equal to 1. So we just get 1 divided by cos squared x, or sec squared x. So that's 3 trigonometric functions done. Still we have 3 to go. And I'm just going to tell you the formula. The derivative of sec x is sec x tan x. The derivative of cotan x is minus cos sec squared x. And the derivative of cosec x is minus cosec x cotan x. It's possible to use the quotient rule to prove these 3 rules. And we might ask one of them in an exam. These are nice exam questions. So I recommend that you try to write down the proofs of these 3 when you do your studies. You should be able to do all of these. Just in case I do decide to ask one of these on an exam, be ready for it. The idea is the same as the previous proof. Just use the quotient rule and just use what you know about sine and tan. For example, find y double prime is if y is equal to sec x. We're going to do 2 derivatives of sec x. And I've written the formula that we need in the yellow box at the top. The derivative of tan x is sec squared x, and the derivative of sec x is sec x tan x. So y prime, just the derivative of sec x. You can see from the yellow box, that's just sec x tan x. And then we're going to differentiate this a second time. Because we have function divided by function, we're going to be using the product rule. Derivative of sec x multiplied by tan x plus sec x multiplied by the derivative of tan x. Again, look to the yellow box. We have the formula that we need there. That's sec x tan x multiplied by tan x plus sec x multiplied by sec squared x, which simplifies to sec x tan squared x plus sec cubed x. We can do limits involving sine and cos as long as we're careful that we're not doing divided by 0. So, for example, this limit, if we just replaced x by 0, we do not get 0 on the bottom. So that's what we'll do. Just replace the x by a 0. We get square root of 2 plus sec 0 divided by cos of pi minus tan 0. And that is just minus root 3. Our second section for this week is the chain rule. What about if we have a function like this? Sine of x squared minus 4. How do we differentiate functions like this, where we have a function of a function? The answer is we use the chain rule. Let me give the theorem first, and then I'll explain how we use it. Suppose that y is equal to f of u is differentiable at the point u, which is g of x, and let's suppose g of x is differentiable at x. So we have a differentiable function of a differentiable function. Then f composed with g is differentiable at x, and we have a formula which tells us how to calculate its derivative. The derivative of f composed with g at x is f prime at g of x multiplied by g prime at x. But personally, I think it's easier to remember the chain rule if we use Leibniz notation. If we use Leibniz notation, then the chain rule is dy dx is equal to dy du multiplied by du dx. And this makes sense to me because if we think dy du as dy divided by du, it's not really dy divided by du, it's really the derivative of y with respect to u. But if we pretend that dy du is dy divided by du, and if we would pretend that du dx is du divided by dx, then we can imagine that we can cancel out the du's and then just be left with dx. We can imagine we have 3 cogs. The right-hand cog turns. It turns an intermediate cog, which turns the left-hand cog. By understanding each one of these derivatives, we can understand the whole movement or the whole system. So, for example, differentiate y is equal to sine of x squared minus 4. We're going to use the chain rule, which I've written in the yellow box at the top. Here we have a function of a function. We have y is equal to sine of u, where u is the function x squared minus 4. Now, both of these are easy functions. We know how to differentiate these two functions. The derivative of sine is cos, so dy du is just cos u, and the derivative of x squared minus 4 is just 2x. The chain rule says we multiply these two functions together. dy dx is dy du du dx. So that's cos u multiplied by 2x, or 2x cos u. We're not finished. We don't want to have a u in our final answer. The question was about y and x. So in our final answer, we shouldn't have any u, we should just have x. But that's okay, because we know that u is x squared minus 4. So we'll just put this in place of u. The answer is dy dx is equal to 2x cos x squared minus 4. And in mathematics, when we use a rule, it's important that we say which rule we're using. If we use the chain rule, then it's important that somewhere in our answer we write by the chain rule. And if I was marking this, there would probably be 1 point for writing by the chain rule. Let's say this is a 10-point question. Then just for writing by the chain rule at the end, I would allocate 1 point for that. In any exam question, if you use a rule or something with a name, say that you're using it, because there might be points for saying that. What do you mean when you say, can we write more than one answer? Next example. Differentiate sine of x squared plus x. One more question in the chat. In the exam, you will ask us how to get the derivative of cos and the other angles, I imagine, functions. We might do. Be familiar with it. I'm more likely to ask tan, cotan, sec, cosec than to ask sine or cos, but it's possible. To answer this question, first thing to do is we need to choose a u. So I'm looking at my problem. I'm looking at sine of x squared plus x, and I see I have an x squared plus x here. Let's call this u. So the first part of my answer is going to be let u be x squared plus x. Then we can use the chain rule, because the derivative of sine x squared plus x is, here y is the same as sine of x squared plus x, d du of sine u multiplied by du dx. Derivative of sine is cos. The derivative of x squared plus x is 2x plus 1. I don't want a u in my final answer, I only want x's, so the final answer is 2x plus 1 cos x squared plus x. Sometimes we need to use the chain rule 2 times or more to solve a problem. This time we're going to have to use the chain rule 2 times. Differentiate g of t is equal to tan of 5 minus sine 2t. So what do we do first? First, we choose a u. I'm looking at my function. I say I have a 5 minus sine 2t here. So that looks about right. I'm going to let u be 5 minus sine 2t. Because then gt is just tan u. And I know how to differentiate tan u. So dg dt by the chain rule is dg du dt, or sec squared u multiplied by the derivative of 5 minus sine 2t. But this is a little bit difficult. I'm going to have to use the chain rule again to calculate this orange derivative. I'm going to need to choose a new function. I've already used u, so let's choose a new letter. And it doesn't matter which letter you use. Choose any letter that you want to use. I'm going to use the letter W. I'm going to let W be equal to 2t. So just looking at the orange part, derivative of 5 minus sine 2t, that's ddw of 5 minus sine w multiplied by dw dt, which is minus cos w multiplied by 2. And then substitute back in to get the final answer. Minus 2 cos 2t, sec squared of 5 minus sine 2t. Let me repeat this answer. I'm starting with tan 5 minus sine 2t, and I want to split this into two functions. I want a function of a function. So I choose u is 5 minus sine 2t, and then gt is tan u. And I get down to dg dt is sec squared u multiplied by ddt of 5 minus sine 2t. At this point, I need to use the chain rule another time. So now I'm looking at my function 5 minus sine 2t, and again, I want this to be a function of a function. So I'm going to need to choose a new letter. Choose any letter that you want. I've already used u, so I can't use u again, so I need a different letter. I'm going to choose w. Looking at 5 minus sine 2t, I choose to have w is equal to 2t, because then that becomes 5 minus sine w. Instead of doing ddt of 5 minus sine 2t, I'm doing ddw of 5 minus sine w multiplied by dw dt. This is just using the chain rule a second time. The derivative of 5 is 0, the derivative of minus sine is minus cos, and the derivative of 2t is 2. So we end up with our final answer. As I said before, the final answer should not have any of these temporary or intermediate variables in it. The question started with y is equal to a function of t. So g is a function of t, so the answer should just be a function of t. We shouldn't have u or w in the final answer. Let's talk about the chain rule with powers of a function. Let's suppose that f is a differentiable function of u, and let's suppose that u is a differentiable function of x. And let's suppose we have that y is equal to f of u. Then the chain rule says ddx of f of u is equal to f prime of u du dx. And that would work for any differentiable functions, but I want to specialize it to just thinking about f of u is equal to u to the power n. Then the derivative of this, f prime, would be nu, n to the power n minus 1. Put these into the chain rule, and we have our formula that ddx of u to the power n is equal to n, u to the power n minus 1, du dx. The next few examples are about using the formula in the box. So I'm going to take this formula and I'm going to put it up the top in a yellow box. I want to differentiate 5x to the power 3 minus x to the power 4 all to the power 7. We have a function u to the power 7. And the formula in the yellow box says it's going to be 7 u to the power 6 multiplied by du dx. So that's 7, 5x to the power 3 minus x to the power 4, all to the power 6, multiplied by the derivative of u. Or 7, 5x cubed minus x to the power 4, all to the power 6, multiplied by 15x squared minus 4x cubed. Let's do another one. We can differentiate 1 divided by 3x minus 2 in two different ways. We could use the quotient rule, because this is a function divided by a function, but it's going to be easier if we use this version of the chain rule, because this is the same as the derivative of 3x minus 2 to the power minus 1. So I have a function u to the power minus 1. And the formula at the top says that's minus 1 multiplied by u to the power minus 2 du dx. So that's minus 1, 3x minus 2 to the power minus 2, multiplied by d dx of 3x minus 2. And that simplifies to minus 3 over 3x minus 2 squared. I'm going to repeat the problem on slide 27. Okay, I want to do the derivative d dx of a function u to the power 7. And I'm going to use the formula in the yellow box at the top, which is a version of the chain rule. This is a chain rule for powers of functions. This says the derivative of u to the power n is n. Well, for us, n is 7, so we can write 7. And then we have u to the power n minus 1. For us, n is 7, so n minus 1 is 6. So that's u to the power 6 multiplied by du dx. So for us, for our example, u is the function 5x cubed minus x to the power 4. So it's going to be 7, and then u to the power 6, 5x cubed minus x to the power 4 to the power 6, multiplied by du dx, which for us is d dx of 5x cubed minus x to the power 4. The derivative of 5x cubed is 15x squared, and the derivative of x to the power 4 is 4x to the power 3. Let me repeat slide 28 again. Again, we have the derivative of u to the power n. Here I have d dx of u to the power minus 1. So looking at the formula of the yellow box, first we have n, so that's -1. And then we have u to the power n minus 1. So for us, that's u to the power -2. And then multiply that by du dx. So -1, and then u to the power -2, and then du dx. And there's a typo here. This 2 should have been a number 3. Let's do another one. The derivative of sine to the power 5 of x. So this is a question where we have u to the power 5. So by the formula, that becomes 5 u to the power 4. So 5 sine to the power 4x, and then multiplied by du dx, multiplied by the derivative of sine x. Differentiate the absolute value of x. So I'm starting by saying, since the absolute value of x is the square root of x squared, let me justify that. If x is 3, we get square root of 3 squared, square root of 9, which is 3, which is the same as the absolute value of 3. But if x is -3, if I do -3 squared, and then I take its square root, that's the same as square root of 9 or 3, which is again the absolute value of -3. Square root of x squared is always the same as absolute value of x. Now, as long as x is not equal to 0, we can use the formula in the yellow box. Because square root of x squared, we can think of as square root of u, where u is x squared. So that's the derivative of the square root of u multiplied by the derivative of x squared. And the derivative of the square root of u, or thinking of it as u to the power of a half, is 1/2 square root of u. And the derivative of x squared, of course, is just 2x. The 2 cancel, we get x over square root of x squared, or x divided by absolute value of x. If x is which is the last step? Okay, so by the chain rule, this is the same as the derivative of square root of u multiplied by the derivative of x squared. Derivative of x squared is an easy one. That's just 2x. The derivative of the square root is one that we've done before. The derivative of the square root of u is 1/2 square root of u. If you look back through previous lectures, we've done this in 2 different ways. I'm going to repeat just one of them here. Square root of u is the same as u to the power a half. So then the derivative of square root of u is the same as the derivative of u to the power of a half. That's a half u to the power, and then we decrease the half by 1 to minus a half. Or 1 over 2. U to the power minus a half is the same as 1 divided by the square root of u. And then that simplifies to x divided by the absolute value of x. If x is a positive number, then x and absolute value of x are the same thing, so we just get 1. For example, we get 4 divided by absolute value of 4, which is equal to 1. But if x is a negative number, then the absolute value of x is equal to minus x. So we get x divided by minus x, which is minus 1. Another example. Show that the slope of every line tangent to the curve y is equal to 1 over 2x cubed is positive. Now, this is the same as this question. Let y be 1 over 1 minus 2x cubed, as long as x is not equal to a half. Show that dy dx is always strictly positive. So the first thing to do is to differentiate this function. We're differentiating 1 minus 2x to the power minus 3. We have u to the power minus 3. So by the formula in the yellow box, it's minus 3 u to the power minus 4. So minus 3, 1 minus 2x to the power minus 4. And then we multiply it by the derivative of 1 minus 2x. And after simplifying, we end up with our answer 6 divided by 1 minus 2x to the power 4, assuming that x is not a half. Now, if x is not a half, that means 1 minus 2x is not 0, and a non-zero number to the power of 4 is always going to be strictly positive. And 6 is strictly positive. So we have positive number divided by positive number, and that's positive. I have one more idea before we take a break. I want to answer the question, why do we use radians in calculus? This is power 4. We start with power 3, and then when we differentiate, power to the minus 3 decreases to minus 4. So the derivative has power 4 in. Why do we use radians in calculus? Remember that we've seen that the derivative of sine is equal to cos, but this is only true if we use radians, because we relied on the limits, which only worked if we use radians. So my question is, what happens if we use degrees instead? Now, remember, radians means the distance around the outside of a circle of radius 1. So from this semicircle, we can see that the distance around the outside of the semicircle is pi. So pi radians must be the same as 180 degrees. So 1 degree must be the same as pi divided by 180 radians, or x degrees must be the same as pi x divided by 180 radians. So if we're doing the derivative of sine x degrees, what that really means is doing the derivative of sine of pi x over 180. And by the chain rule, that's pi over 180 cos pi x over 180, or pi over 180 cos x degrees. So we have the choice. We could use radians and we could have this nice easy formula, or we could use degrees and we could have this not so nice formula with this extra term that we would have to keep track of. And then if we were doing something complicated, some complicated calculations, we're going to end up with lots and lots of pi over 180s, and it's going to lead to errors, possibly. So this is why we use radians in calculus. We use it so that we have a nice, simple formula to remember. The derivative of sine is equal to cos. Now I'm going to take a 10-minute break, and we'll continue at, let's say, 1 minute past 3. Our third and final topic for this week is implicit differentiation. And implicit differentiation seems to scare calculus students, but I don't know why. It really shouldn't. Implicit differentiation is just the chain rule. There's a typo here. There's not going to be much new or different in this section. We're just going to be using the chain rule again and again and again. For example, find dy dx if y squared is equal to x. I'm going to solve this in two different ways. The first way does not use implicit differentiation. The first way we could solve this problem is to think of this as two different functions. y1 is equal to square root of x and y2 is minus square root of x. And then differentiate each of these functions separately. The derivative of y1 is 1 over 2 root x, and the derivative of y2 is 1 over 2 root x. Now let's solve this again, but this time I want to use implicit differentiation. And I'm going to show you the key step, the key idea in this section. We're going to start with our equation. We're starting with y squared is equal to x. And we're going to differentiate both sides of this equation. If y squared is equal to x, then the derivative of y squared must be equal to the derivative of x. And that's it. That's the only new idea in this section. That shouldn't scare you. Start with an equation and write d dx on both sides. There's nothing unusual or difficult there. The derivative of x is just 1. So now let's look at the left side. d dx of y squared. Now it's time to use the chain rule, because d dx of y squared is the same as d dy of y squared, dy dx. That's just the chain rule, nothing new there. And the derivative of y squared with respect to y is 2y. So we have 2y dy dx is equal to 1. Divide both sides by 2y and we get our answer. Dy dx is equal to 1 over 2y. Now, this is the same as the answer that we got using solution 1, because if y1 is the square root of x, then 1 over 2y is 1 over 2 square root of x. And if y2 is minus square root of x, then 1 over 2 y2 is 1 over 2 minus square root of x, or minus 1 over 2 root x. So let me just recap. What is implicit differentiation? It's just step 1, differentiate both sides of an equation. That's easy. Step 2, use the chain rule. You know how to do that. That's not too hard. In all of the examples in this section, this is what we're going to be doing. We have an equation. We're going to differentiate both sides, and then we're going to use the chain rule. For example, find the slope of the circle x squared plus y squared equal to 25 at the point 3 minus 4. So we're going to use implicit differentiation. We're going to start with our equation. We're starting with x squared plus y squared is equal to 25. We're going to differentiate both sides, and then we're going to use the chain rule. So start with our equation and then differentiate everything. d dx of x squared plus d dy of y squared is equal to d dx of 25. d dx of x squared, of course, is just 2x. d dx of y squared. For this, we need to use the chain rule. That's 2y dy dx. And then on the right side, derivative of a constant is just 0. Rearrange that and we get dy dx is minus x divided by y. So let me say that again. We start with the equation and we differentiate everything. And then we use the chain rule and then we rearrange. Now we're interested in the slope at the point 3 minus 4. So we want dy dx at the point 3 minus 4, or minus x divided by y at the 3.3 minus 4, which is just 3 divided by 4. So let's go back to the picture. I'm saying the slope of this green line is 3 divided by 4. Does that look about right? Yeah, from the picture, that looks like it's about right. Another example. Find dy dx if y squared is equal to x squared plus sine xy. So we have an equation and we're going to use implicit differentiation. We're going to differentiate both sides of the equation and then we're going to use the chain rule. So we're starting with d dx of y squared is equal to d dx of x squared plus d dx of sine xy. So let's do that. On the left side, d dx of y squared by the chain rule is 2y dy dx. This is the bit where we're using the chain rule. And then derivative of x squared is 2x, that's easy. And then chain rule again, the derivative of sine xy is cos xy multiplied by the derivative of xy. Now we're not finished yet because we still have a derivative that we need to do. We have a function multiplied by a function. So now we need the product rule. Differentiate one of them and leave the other one as it is. So differentiate the x to get 1, leave y as it is, and then do plus, leave the x as it is, and then differentiate the y, dy dx. Just product rule here. After that, we've done all the differentiation that we need to do. Now it's just a case of rearranging this so that we get dy dx is equal to something. Let's put all of the dy dx terms on the left. I have a 2y dy dx and I have a cos xy x dy dx. And then divide both sides by 2y minus x cos xy to get the answer. dy dx is 2x plus y cos xy divided by 2y minus x cos xy. So let me repeat that. Start with the equation, differentiate each term, chain rule and then product rule. And then after that, everything is just rearranging. Let's do another one. Find d squared y dx squared, so that's the second derivative of y with respect to x, if 2x cubed minus 3y squared is equal to 8. So we're going to start with our equation, and because I'm going to be dividing by y later, so let's just make sure that we have y not equal to 0. I'm going to take this equation and I'm going to differentiate both sides. So on the left we have 6x squared minus 6y y prime is equal to 0. Rearranging this, we find that y prime is equal to x squared over y. So that's the first derivative, but we want the second derivative, so we're going to need to differentiate it again. So we're going to differentiate y prime is equal to x squared over y. This is a quotient rule differentiation. So derivative of u over v is u prime v minus uv prime divided by u squared. So for us, it's derivative of x squared gives us 2x, and then y stays as it is, minus x squared over y, sorry, x squared y prime divided by y squared. Question in the chat, why is there a y? Do you mean just here? Or y, or are you writing y prime? Okay, so let's go back to slide 44. Why is there a y prime here? So I'm differentiating 2x cubed to get 6x squared. That's the easy part. I'm also differentiating 3y squared, but with respect to x. So it's d dx of 3y squared. And by the chain rule, that's the same as d dy of 3y squared multiplied by dy dx, or derivative of 3y squared, which is 6y, multiplied by y prime. And then I want to use the quotient rule to get the second derivative. So we can get to 6xy minus x squared y prime divided by y squared, which simplifies a little bit to 2x over y minus x squared over y squared multiplied by y prime. But we know y prime. We know that y prime is x squared over y. So we can substitute that in. 2x over y minus x squared over y squared multiplied by x squared over y. That simplifies to 2x over y minus x to the power 4 over y cubed. Now, previously we talked about tangent lines. Now I want to introduce a new type of line called a normal line. A normal line passing through a point P is the line which is perpendicular to or orthogonal to a tangent line. So in other words, it's where the angle here is 90 degrees or pi over 2 radians. And the rule is, if a tangent line has slope k, then the normal line has slope minus 1 divided by k. So for example, if a tangent line has slope 7, then the normal line has slope minus 1 divided by 7. So if you know how to do a tangent line, and if you know this rule, that you replace the slope k with minus 1 over k, then you can do normal lines. Show that the point 2, 4 lies on the curve x cubed plus y cubed minus 9x xy is equal to 0. Then find the tangent and normal to the curve there. So first of all, does this point really lie on this curve? I'm going to calculate x cubed plus y cubed minus 9xy with x equal to 2 and y is equal to 4. And then the question is, do we get 0? So let's try that. Put x equal to 2. Put y equal to 4. 2 cubed plus 4 cubed minus 9 times 2 times 4. 8 plus 64 minus 72. And yes, we do get equal to 0. So the point 2, 4 does lie on this curve. And then the example says, find the tangent and the normal to the curve there. First thing to do is to find the slope of the curve at the point 2, 4. So we're going to be doing implicit differentiation. Start with the equation and then differentiate everything. So that's 3x squared, and then the derivative of y cubed with respect to x. 3y squared dy dx minus the derivative of 9xy. So that's product rule, because we have function multiplied by function. X dy dx plus y dx dx. After rearranging that, we get our formula for dy dx, or y prime if you prefer. 3y minus x squared divided by y squared minus 3x. I know I'm being quick on this slide. You can come back and check the details here later. We are interested in the slope at the point 2, 4. We want dy dx at the point 2, 4. So we replace the x's by 2's and we replace the y's by 4. And please check when you look at this later. we find that the slope is 4/5. So that means the tangent line has slope 4/5. And then the rule is, if the tangent line has slope k, then the normal line has slope -1 divided by k. If the tangent line has slope 4/5, then the normal line has slope -5 divided by 4. It's always multiply it by -1 and then do 1 divided by that number. Now we know how to do tangent line. We take the number 2 and we write x minus 2, multiply that by the slope, and then we take the value of y there and we put that at the front. 4 plus the slope multiplied by x minus 2. And that simplifies to 4/5x plus 12/5. For the normal line, we do the same thing. The only difference is we have a different slope. So still, y is equal to 4, and x is equal to 2. So it's still going to be 4 plus something multiplied by x minus 2. What is the something? The something is the slope. 4 minus 5/4, x minus 2. The only difference between the tangent line and the slope and the normal line is that we have a different slope, because they both pass through the same point. They both pass through the point 2, 4. And I'm going to finish by showing you a picture of this. The blue curve is our curve x cubed plus y cubed minus 9xy is equal to 0. The tangent line in red is y is equal to 4/5x plus 12/5. And the green line, the normal line, is y is equal to minus 5/4x plus 13/2. And then we come to the end of this week's lesson. Next week, we're going to finish chapter 3 and start chapter 4. We'll talk about related rates, linearization and differentials, extreme values of functions on closed intervals, and the mean value field. Depending on the topics on the syllabus, some weeks we will have longer lessons and some weeks we will have shorter lessons. This week was one of the shorter lessons. Are there any questions?